branch of physics that deals with the magnetism due to electric current is called as electromagnetism. From these observations, what can we say? That the moving charge is a source of both electric field as well as magnetic field. So what is the meaning of superposition principle for magnetic field? It is nothing but the magnetic field of several sources, and it is the vector addition of magnetic field of each individual source. So the symbolical convention of the direction of current is depicted by cross and dot convention. Hello everyone, welcome to session 1 of chapter 4, Moving Charges and Magnetism. This is Swati from Department of Physics, Vidyashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, till last chapter, that is in electric charges and fields, electrostatic potential and capacitance, and in current electricity, we have studied about the static charges and moving charges. So what are the mechanism of static charges and the moving charges we have studied, and how does the moving charges produces an electric current we have studied from current electricity. We have also studied about the measurement of electric current and what are the effects of temperature in the study of current. And in this chapter, we are going to study about the magnetic effects of current and magnetism concepts and various phenomena that are involved in magnetism. And we are also studying about the moving charges or electric current. How do they produce a magnetic field in the surrounding space? Because in the previous chapter, we have studied the charges were producing a current in a space, and now we are studying about the moving charges and electric charges. They are producing a magnetic field in their surrounding space. So let us now begin with the first concept, that is Oersted experiments. Oersted's experiment is one of the basic concepts which gave us an idea about the interconnection between the current and magnetism. So electricity is a separate branch and magnetism is a separate branch. So it has been known for the people about the electricity and magnetism since many years. But just 200 years before, a person called Oersted accidentally proved that the electric charges or the current can even produce a magnetic field by his demonstration. So what did he prove then? So let us see his studies and observations one by one. So in 1820, the Danish physicist Hans Christian Oersted, in his experiment, he proved that the current in a circuit or current in space can even produce a magnetic field. So he was doing some demonstration with the help of current, and he observed that the deflection in a magnetic needle when it is placed next to a wire which is carrying a current. So that is his first experimental observation. Current in a straight wire caused a noticeable deflection in a magnetic compass when it is held near the wire. So he was doing an experiment with a wire. Say for example, this is a wire, and he observed near his wire, because this wire was carrying a current, and he observed there is a deflection in the needle of the compass. He also observed many things to conclude how they are related with each other. So he found that the magnetic needle is aligned tangentially to an imaginary circle which has a straight current carrying wire as its center. For example, here it is a straight current carrying circle. The needle tends to align to an imaginary circle tangentially. That was his another observation. And he also noticed that if the direction of the current is reversed, then the direction of the needle also reversed. You can see here, the first diagram is showing that the wire, there is a current carrying conductor which is at its center, and it is also a plane perpendicular to the wire. I mean, the tangential observation, what he is observing is plane perpendicular to the wire. And he also observed that the deflection increases on increasing the current or bringing the compass or bringing the magnetic compass needle close to the wire. As the compass is held nearer and nearer to the wire, the deflection was increasing. So that was another experiment. If the iron fillings are sprinkled around the wire, they tend to arrange themselves in concentric circles with the wire as its center, and we have shown that in the diagram C. You can see here, suppose if the iron fillings are sprinkled all over and if the wire is kept in between and which is current carrying wire, then due to the magnetic field produced by a wire, the iron fillings are tend to align themselves in a concentric circles, which is another proof for his experimental observation for the interconnection of electricity and magnetism. The magnetic field disappears when the circuit gets switched off, or as soon as the current is switched off, the magnetic field disappears. So here what can we say from this? When there is a current, there produces a magnetic field. When the current is switched off, the magnetic field disappears. So these are the major observations from Oersted, and hence he concluded that the moving charges or current produces a magnetic field in the surrounding space. Not only Oersted, but also there are other scientists who supported Oersted for his experimental observations, and one of them are Ampere. So Ampere also supported this observation, and we all know about the unification of laws. Maxwell is one of the other scientists who supported this Oersted experiment, and he also unified the laws of electricity and magnetism, and he developed a new field of physics called as electromagnetism. So what is electromagnetism? The branch of physics that deals with the magnetism due to electric current is called as electromagnetism. Electromagnetism is a branch which consists of electricity as well as magnetism. So this is a brief introduction about how does the theory of electromagnetism develops. Let us now understand about some basic laws or principle or some basic terms related to magnetism. So let's start with magnetic force. What is the meaning of magnetic force? It is a force experienced by a moving charge particle. We know that the moving charge particle or moving current produces magnetic field. So the force experienced by moving charges or a current carrying wire in a magnetic field is called as magnetic force. We all know that from electrostatics, we have learned that a static charge, which means a charge which is at rest, produced an electric field around it. Or we can also say that an electric charge which is at rest or a static charge is a source of electric field. A static charge used to produce an electric field E, we denote electric field as E at every point in the space around it. So at any point if a charge Q is placed, it experiences a force of F is equal to Q into E is what we have already studied. We have also studied about the vector addition of all these electric fields if there are more than one charges with the help of superposition principle. So this is the basics of electric charges we have already studied in the previous chapters. Now let us understand the phenomenon of magnetism in the same way. So as static charges produces an electric field around it, the current carrying conductor or moving charges also produces magnetic field in the space around them. So this magnetic field is denoted by B. We have denoted electric field with the help of a letter E, and the magnetic field is denoted by B. This is the basic thing which we have to know because we will be oftenly using B throughout the chapter. So we have even learned that the magnetic field disappears as soon as the current is switched off. So from these observations, what can we say? That the moving charge is a source of both electric field as well as magnetic field. So this magnetic field B is a vector quantity. So what is the meaning of superposition principle for magnetic field? It is nothing but the magnetic field of several sources, and it is the vector addition of magnetic field of each individual source. So these magnetic field lines are closed paths. Let us understand some of the indications in the study of magnetism. What are those indications? A current or a field. Here field means the magnetic field. An electric current or a magnetic field emerging out of the plane, then it is depicted by a symbol that is dot. Say for example, we have cross and dot conventions in the study of magnetic field. Now, if a current is coming out of the plane, if this is a plane, if the current is coming out of the plane, then it should be depicted by a dot convention. And if a current or a field means the magnetic field going into the plane of the paper or into the plane perpendicularly, then it is depicted by a cross symbol. So the symbolical convention of the direction of current is depicted by cross and dot convention. So these are the two things which we have to keep in mind in the study or in understanding the diagrammatical or the schematic representation of the magnetic field concepts. So let us consider a charge Q which is moving with a velocity v in the presence of magnetic field, and the magnetic field is denoted by B. Now it is experimentally found that the magnetic force on a charge is given by F is equal to Q into V cross B. This is a cross product of velocity and the magnetic field, or it can be written as QVB sine theta into n cap, where n cap is a unit vector. So what is theta? It is nothing but the angle between the velocity and the magnetic field. So this magnetic force on a moving charge has few of the features. So let us study what are the features. So the magnetic force F depends on charge of a particle Q, and it depends on velocity. It also depends on magnetic field B. So how to say that? With the help of this expression. Force depends on charge, it depends on velocity, it also depends on magnetic field. And the force on a negative charge is opposite to that on a positive charge. What is the force that is on positive charge when it is moving? It is negative, or it is opposite on a negative charge. So the expression of force F is equal to QVB sine theta includes a vector product of V, that is velocity, as well as the magnetic field B. The direction of force is perpendicular to both the velocity and the magnetic field. But the velocity and the magnetic field need not to be perpendicular always, but the force is always perpendicular to both the velocity and the magnetic field. When can we say the force on a moving charge is zero? So the force due to a magnetic field is zero if the velocity and the magnetic field are parallel or anti-parallel. If the velocity and the magnetic field are parallel, if the velocity and the magnetic field are anti-parallel, then we can say the force is zero. That is, when theta is equal to 0 in this condition, when theta is equal to 180 degree, so the value of F will be equal to 0. F is equal to QVB sine theta when the angle between V and B is 90 degree, which means when they are perpendicular. That is, when theta is equal to 90 degree, sine 90 is equal to 1, and F is equal to QVB we will get. So that is the maximum force what we can get when the angle between F and B is 90 degree. So the force is 0 if charge is not moving. If the velocity of charge is 0, when the charge is not moving means the velocity is 0. So when V becomes 0, the force will also be 0. Only a moving charge experiences a magnetic force is what the basic concept we need to understand. So we all know the expression for magnetic force, that is F is equal to QVB sine theta into n cap. So when can we say this F, that is the force which is equal to the magnetic field, when the value of Q becomes 1 coulomb, that is the charge of 1 coulomb, and the velocity becomes 1 meter per second, and the value of theta becomes 90 degree. So we can say the magnetic field at a point is defined as the force acting on a unit positive charge and moving with a unit velocity, and the velocity is perpendicular to the direction of magnetic field. So the value of theta is 90 degree and the velocity is 1 meter per second, and it is acting on a unit positive charge. We can say F is equal to B. Now what is the SI unit of magnetic field? It is Tesla, or it is denoted by capital T. How to define 1 Tesla? So the magnetic field is said to be 1 Tesla if a positive charge, that is 1 coulomb, moving at right angles, that is 90 degree to the magnetic field with the velocity of 1 meter per second. So Tesla is one of the unit of magnetic field, which is a very large unit. We can also use a smaller unit to find the magnetic field, that is Gauss. The value of 1 Gauss is equal to 10 power minus 4 Tesla. The Earth's magnetic field, the value of Earth's magnetic field is 3.6 into 10 power minus 5 Tesla. So these are some of the important things which we have to know in the study of magnetic field. Let us now study one more important concept, that is Lorentz force. Lorentz force generally deals with the total force. So what are the total force? What forces then that acts on a charge? Let us understand. In the presence of both electric field and magnetic field, a point charge Q which is moving with certain velocity V, then the total force on that charge is called as Lorentz force. Total force is denoted by F vector, which is equal to sum of the force due to electricity and the force due to magnetic field. So what is force due to electric charges? That is F is equal to QE, and the magnetic force F due to magnetic field, and when the charge is moving with certain velocity, it is given as F is equal to Q into V cross B, as we have already studied. So it is sum of force due to electric current and force due to magnetic field. So F is equal to QE plus Q V cross B, or we can write it as F is equal to Q is the common term, we can take common and we remain with E plus V cross B. What is F here? It is nothing but the Lorentz force, because total force, that is called as Lorentz force, and E is nothing but the electric field, and Q is the charge, V is the velocity, B is magnetic field. Suppose if I have a current carrying conductor of certain length, then how to calculate the magnetic force? So the magnetic force on a current carrying conductor of length L is calculated with the help of this formula, that is F is equal to I into L cross B, or we can write it as F is equal to ILB sin theta, where I is the current in a conductor, L is length of the current carrying conductor, and B is the magnetic field. Let us now understand how to get this expression. Let us derive. In today's session, we have learnt about the basic concepts about the magnetism, how the electricity and magnetism are unified, how they are interrelated with each other, and also we have learnt about some basic concepts, terms which are related to magnetism. In the upcoming sessions, let us learn some more interesting concepts. See you all in the next session. Keep learning, all of you. Thank you.